Okay, are my slides coming through? Can everyone see that?
Yes. Yes, we can see your slides.
Okay, you can see the slideshow, correct?
Yes, that's correct.
Okay, cool. Sorry, I'll get started then. Hello all. My name is Sam Dawson. I'm a PhD candidate at the University of Kent. The paper I will be presenting today is titled Chronos versus Chaos, Timing Weak Memory Executions in the Linux Kernel. First, I'll walk you through some of the key motivations behind my research before moving on to a quick discussion of the tool we're building to enable our research, and then finally move on to some of the results we've gathered. I must point out development is still very much work in progress on this tool. But I think what we've uncovered so far is fairly interesting, even if it has not yet resulted in new speculative attacks. So, without further ado, why should we care about timing weak memory executions in the Linux kernel? First off, I'll provide some context on the work. If we think about the x86 architecture, there's probably a multitude of attacks you can come up with that the architectural specifications enable. There's also a bunch of mitigations you could probably name: non-executable memory regions, address space randomization, canary addresses, and so on. When we think about the x86 architecture, we're in a world where you can write code, manipulate memory, and observe the outcomes. It would be a fair assumption to make that the implementation of that architecture isn't your concern as a programmer. As long as it conforms to the ISA, that's all you as an attacker or a defender need to worry about. When you're looking at the ISA, you're looking at the bedrock from which all security assumptions are made. Unfortunately, much to the chagrin of, well, just about every computer user on the planet, this is not actually the case. So when we dive below the architecture, we enter a world where memory moves fast and breaks rules in the name of efficiency. Say, for instance, that the memory pipeline, are waiting around for a memory access from DRAM that hasn't returned yet. Now, there's dependencies on this memory access that mean we can't skip past it and process instructions further down the chain. Without knowing what the value of this memory access is, we cannot continue. The pipeline stalls. Well, on modern architectures, that's fine, actually. We'll just assume that the access we're making, it will return the same value as it did last time. Chances are that we're probably right and the value hasn't changed. Now, if we are right, we can continue to resolve instructions dependent on this access without waiting around for the return value. Eventually, we find out what was in the memory address. We speculated correctly in this case. We can retire these instructions and their effects become visible to the architecture. If we aren't correct, if we've guessed wrong, we turn the clock back and start processing these dependent instructions again with the right value from memory this time. So we roll back to that checkpoint and we start again. As long as it's correct by the time we retire this instruction at the end of the memory pipeline, the architectural specifications are satisfied. So speculating in this way is harmless, right? This happens below the architecture. So the user shouldn't be able to even observe these behaviors, let alone use them to break security policies. But yeah, again, this is not the case. The fundamental problem with speculative execution is time. We want our CPU to be constantly doing the maximum amount of work it can. Idling while we wait around for costly DRAM accesses is not an efficient use of the processor's time. This is where the cache comes into play. By keeping a subset of the most recently used addresses and their values in a memory segment that can be accessed much more quickly than DRAM, we can cut down on the time it takes to access an address and observe its value. If we think about this in another way, we can see that there is an observable difference in return time between an access made to an address that is served by the cache and an access made to an address that is served by main memory. This simple differential gives us a window into the internals of the machine, allowing the user to infer knowledge about the state of memory that a programmer might expect to be kept secret. So, for example, if we had a memory mapping of the functions for primitive operations in the code base that handles RSA key generation, this could be used to carry out a side channel attack. While one user on a machine is generating their RSA private key, another user in a separate memory space on the same machine could run code that observes when those memory addresses are loaded into the cache, which would tell them which function is being loaded, and thus undermine the security of the RSA key if you map out the entirety of the function accesses during generation. I'm sure you can imagine many more situations in which security on a system completely falls down when users are able to observe memory that they shouldn't. So we know that the microarchitecture sometimes does dangerous things from a security perspective, but it's fine, right? Because nobody can see what it's up to. We also know that measuring the time of memory accesses under certain conditions allows us to observe the state of the cache and thus gives us a window into the memory accesses the microarchitecture is making. You can see the problem here, right? This is the essence of the spectrum meltdown attacks. Without diving too deeply into the meat of these attacks, you can think of Spectre category attacks as ones that break software level security assumptions, such as using speculative execution to pass a value into a control block that the control statement would normally disallow. Meltdown style attacks, conversely, take advantage of speculating on accesses that would throw hardware exceptions, such as page faults. In both cases, we can monitor the cache to observe the outcomes of accesses that would be disallowed by some security policy built on top of the architecture. But because we can observe the microarchitecture, we can observe accesses, frankly, that we really shouldn't be able to observe. It should be apparent at this point that understanding the behavior of the microarchitecture is paramount to building countermeasures against these attacks. Remember, these are passive sniffing attacks. They leave very little evidence of having ever occurred in the system. Unless you can, unless you can detect the patterns of memory accesses necessary to pull off one of these attacks in real time with an intrusion detection system, one which can distinguish between legitimate access patterns and patterns designed to massage the cache, there's actually very little, for instance, incident response to go on. Intel and ARM have released patches to mitigate some of the most viable variants of Spectrum Meltdown, and prevention really is the way to go here, which leads us to the core question. How do we detect more of these attacks? Well, we could start thinking about other ways to reason about the hardware, and this is where weak memory comes into play. So there is no major modern architecture which implements a perfectly sequentially consistent memory model for multi-threaded programs. What this means is that without any additional memory barriers provided by the programmer, the architectural memory model may introduce reorderings of instructions that do not constitute a sequentially consistent execution of each thread. In the store buffering example shown, we have two threads working side by side. They'll both be executed after a common spin lock releases them. So what we have here is essentially a data race on variables X and Y. Given the code, our intuition is that one of three things should really happen. The write to X is ordered after the read from X, which would result in x as 0, and therefore y equals 1. And vice versa, this would give us y equals 0 and x equals 1 in a situation where the orderings are reversed. But we can also imagine a third scenario in which both writes to x and y are ordered before both reads. In this case, we would read 1 out of both variables. However, there is a fourth outcome that we can actually observe. We can see that the outcome 0, 0 could only be possible if we made thread local reorderings of the code. But this is allowed behavior according to the x86 memory model, as the initial write in each thread is pushed into the store buffer before it propagates to the cache and main memory. During this propagation time, the reads below would take place. Now, in practice, actually observing this behavior might be quite rare. We can test for this behavior by repeatedly running what we call a litmus test, which encapsulates the core of the behavior we are trying to observe. If we observe 0, 0 in this case, so a read of 0 from x and a read of 0 from y, then we know that store buffering has occurred. The key takeaway here is that elements of the microarchitectural memory pipeline responsible for these reorderings also expose microarchitectural attacks. For the sake of demonstrating kerntime, we focus on the store buffer, which we know has a key role in the speculative store buffer bypass attack. Our goal with kerntime is to use weak memory litmus tests as an oracle, stressing specific pipeline elements that we think are responsible for weak memory behavior to uncover experimental details about the memory pipeline, which could potentially play a role in future speculative execution attacks. The test results you are going to see shortly are a proof of concept, demonstrating that we can effectively gather and process experimental data from deploying these litmus tests inside the Linux kernel. Future work on this project will require combining our results with a cache profiling system to observe speculative execution. So the sort of cache side channel techniques that we were talking about earlier, we intend to deploy them in addition to the store buffering tests we're about to show you. Okay. One moment. Okay, so we can see here that we have a scatter graph that represents two scenarios, right? So our green and yellow pairing are tests we've run and timed in which no store buffering was observed. So for the vast majority of these tests, you can see all of these yellow-green pairs actually indicate that there was no store buffering that occurred. However, for our blue and red pairs, this indicates that store buffering did actually occur. So let's look at the data a little bit more. First of all, we can observe this, this exclusion zone, right, towards the bottom of the chart. So what we've found is that where one thread scores low, another thread will score higher. So generally where we find a thread inside this particular cycle banding, a reciprocal thread will time up in the second band. So if one thread scores anything between 175 to 350 cycles, in this test, the other thread will score roughly between 400 to 700 cycles in terms of execution time. So we can exclude anything that returns below 250 cycles when timed as not displaying store buffering behavior. And we can do this without really knowing anything about the other thread. Yeah, sorry, this indicates that where one thread wraps up quickly, we know store buffering has not occurred. Now I want to focus on this band of store buffering results between 250 and 400 cycles. In this environment, it's clear that either thread returning within this time span is a statistically significant indicator of store buffering behavior. I'm going to move on to a chart in a second, which will make this clearer. But if I zoom in a little bit, oh God, okay, well, I can't do it in the PowerPoint, but you can see anyway that we have this visually distinct highway between 300 and 400 cycles where most of our store buffering results occur. Now, we intend to explore the results of combining this signifier with other aspects, such as the return value of a single thread, to gauge whether or not store buffering has occurred without knowledge of the execution time or the return value of the other thread. It's also quite interesting to note that we see an increased incidence of store buffering towards the beginning of the tests. We're not quite sure what causes this yet, but we suspect it's cache stashing. Although this could be a synchronization effect as the threads settle into temporal sync, we expect the spin lock we use would minimize this effect. It carries out before every single test we run. It's not a one and done thing. We synchronize on spin lock before every single one of these tests. So we want to carry out further testing using cache flushes to see whether or not we can elicit this behavior that we see at the beginning of these tests for a longer duration, which might perhaps motivate increased instance of store buffering behavior all the way through. So again, we can see that this period between 300 cycles and 400 cycles, it's very likely that if one thread returns within that time, or rather we measure the execution of that thread as being within 300 to 400 cycles, we can see that there's actually a very, very high chance that this will be a store buffering result. And again, you can see this exclusionary zone below 250 cycles where store buffering just does not occur. Our other interesting result comes from experimenting with several different methods of recording the time taken per thread. You can see that these results here are absolutely collapsed and quite noisy, but we're not really interested in the banding effect or the timing in this case. What we're actually interested in is the extremely high incidence of store buffering behavior. If we compare back to a previous one, you can see that there's, very little store buffering behavior on the whole. So the environment in which we elicited this amount of store buffering behavior essentially boils down to when we insert the our timer instruction, the RDTSC timer instruction, after our thread synchronizing spin lock instead of before. When profiling the interaction between two threads pinned on logical cores within the same physical core, so we're taking advantage of hyperthreading here, we observe a drastic increase in the number of store buffering results returned. Again, we are unsure of the mechanisms in place that cause this massive uptick in store buffering behavior, but past work on NVIDIA GPUs has shown that it is possible to deterministically increase the incidence of weak memory behaviors using core pinning, resource starvation, and strategic environmental settings. So we hope to explore these avenues more as we bring kerntime to fruition, to full maturity as a profiling tool, and to try and get into the bottom of some of these fairly weird effects that we've noticed. So I'm going to have to ask, I'm happy to field maybe one or two questions quickly, but if you have questions about the talk and you'd like to know more about my work or to question some of what you've seen here, feel free to email me at samgawson at sgd6@kent.ac.uk. Other than that, thank you very much for your time. Yeah, thanks, guys.
All right, so it looks like we have about 9 minutes left for question and answering. So does anyone in the audience have any questions? No? All right, what about in the Zoom call?
Just one question. So which architectures did you explore for this work? Was it Intel and ARM, both of them?
Oh, sorry. So we've noted this in the paper, but primarily Intel.
Okay.
Yeah, so we do have a version of this that is working on ARM architecture. It's fairly easy to port, actually. We just really changed the assembly fragments that we actually deploy to carry out the litmus tests. If I just come back to the store buffering example quickly and bring the slideshow back. Excuse me. Okay, previous, here we go. So this store buffering example here, we actually deploy it inside the kernel with an assembly fragment, or rather two assembly fragments that represent each one of these threads. So we do have an ARM implementation that just uses different assembly payloads essentially to investigate the effects of weak memory on ARM. There is a significantly larger set of interesting weak memory behaviors that are allowed on ARM. So we're currently trying to investigate each one of those behaviors, try and pin them to individual pieces of hardware in the memory pipeline and draw out interesting results of them. So yeah, this work is primarily on Intel x86. We do have an implementation that we're deploying on ARM at the moment, and I hope before my thesis is completed to also bring back some interesting results from running this thing over ARM.
Thank you. Thanks for the information.
No problem.
All right, so is there anyone else with a question?
Thank you for presentation. Could you explain again when might this non-SC outcomes take place, or is that this like probability?
Oh, so individual non-SC outcomes take place. It's a probability thing. So we measure each each execution individually, right? And we capture the execution time on each thread, once it completes. And we also record the, we also record the results of reading out of the registers on those threads. So individually, in our testing, you can observe our red and blue pairs indicate when store buffering has occurred. But you can also determine this probabilistically if you were, if you had a limited set of this information, right? If you were only restricted to knowing the execution time of one thread, as opposed to the execution time and the register results of both threads, you could infer from observing a cycle count within this band between 300 and 400 that probabilistically you're very, very likely to be encountering store buffering behavior.
Okay, so very likely is about like 2%, no, 1% or 10%?
Oh, of incidents in this test. I believe, yeah. So off the top of my head, usually we observe anywhere between about 1 to 3% under normal testing circumstances of non-SC behavior. So about 3%. So in this case, yeah, about 300 of these 10,000 results would be non-SC. I can again, if we had a chat offline, if you send me an email, I can you know, I can give you the exact results. I believe the number is in the paper, but if not, again, I can, you know, we can have a conversation offline, and I can share the results.
Yeah, I see. Thank you.
No problem.